Bismillahirrahmanirrahim. Welcome students to the lecture of digital logic design. In the today's lecture, we will be discussing the binary codes. In the previous lecture, we discussed the binary arithmetic, and in the current lecture, we will be discussing the binary codes. This part of the course belongs to the course learning outcome 1. The binary code we will be discussing today is the BCD code. It's known as the binary coded decimal. It's slightly different from the binary representation. In BCD code, usually we represent number decimal equivalent number from 0 to 9. All of these numbers are represented in a form of 4 bits. Say for example, if we have a 0 here, 0 is represented in 4 BCD bits, while 1 is represented in same 4 bits. Similarly 2, 3, 4, 5, 6 up till 9. You can see that after 9 there are no representation. But if you remember that for a 4-bit combination we can represent a maximum of decimal equivalent of 15. So the remaining bits are unused in this combination. So actually these bits are not used, or these combinations are not used in the BCD representation. Generally for the binary codes, we use a specifically designed you can say a predefined sequence to represent any decimal equivalent number. It could be equivalent to its decimal counterpart in the binary, or it could be different. In BCD case, it's equivalent to 0 and 9, 0 to 9 equivalent of decimal binary equivalent. But you will see there are other codes that in which the numbers may be differ, because if you convert this into binary, it's same. But the limitation is that BCD only represents 9, so 0 to 9 are only represented in this, because we are more accustomed to the decimal number system, so that's why we are always trying to relate the number systems with the decimal meaning. Say if we have a number like this 185, to represent this number in the BCD format, what we do is we have to separately represent each decimal digit. So we have to separately represent 5, we have to separately represent 8, and then we have to separately represent 1. What we do is that for the 5, we write a 4-digit code in binary which represents the number 5. We can just look at this from the table. Is actually the equivalent of binary 5, but it's represented in 4 bits. So this represents 5, this represents 8, and this represents 1. But if you see that in the normal binary representation, the 185 would have been represented in this way. So the BCD representation is slightly different from this one, because in the BCD each digit has to be represented in a predefined sequence, and in this case, the BCD case, this sequence is defined in this table. So in this way we define a BCD code. Now we will see the addition of the BCD numbers. Generally there are many hardware or systems in which we have to use the BCD thing. If you remember, or you will be using this thing in the lab part, the 7-segment display. The 7-segment display is very common hardware, for it consists of 7 LEDs which constitutes a single word, like 1 to 9. So how do we represent any number in this is generally represented in the form of a BCD format. Now we will be discussing the addition part of this BCD thing. In the BCD, as we have discussed, that the maximum number that we can represent is 9. The maximum number we are representing is 9. So what we have to do is that to make it our answer correct, so if we have to add 2 different BCD numbers, what we need to add is we need to add a difference of this and the actual representation in 4 bits, because if you represent any number in 4 bits, you can represent a maximum of decimal equivalent of 15, but in the BCD we can only represent up to 9, because the remaining bits are unused in the BCD sequence. In order to make the result correct, what we do is we add a number of 6 to the each of our result. For example, in this case, we have 8 represented in this way, and we have a 9 represented in this way. Because of the simple decimal addition, this will give us a result of 17. But if you add both of them, you will see that our result is greater than the 9 bits, because 9 are greater than the 9, because 9 is the maximum number that could be represented in a BCD system. But in this case, our result is more than that. It's actually 17. So what we do is to correct a result, we add a 6 to the result. We will add a 6 here. So in this result, we will add 6 here. The equivalent of the 6 BCD is this. We will then perform the addition part. We will get this result here. So actually, this represents now the 7 part here, and this represents the 1. And actually, when we are representing this in BCD, because this is the carry out, we will also represent 3 zeros here. So it is actually 1 and 7. So we will be separately representing the 1 term and the 7 term. And how we do it, we just add a 6 number to the result if the result is greater than 9. Now we will see 2 different numbers. Say we have to add 2 different BCD numbers. One is 184 and other is the 576. What we do is we will add them column by column. So first what we do is we represent each number in form of the BCD. 4 is represented here. Similarly 8 here, 1 here. This is 6. This is 7. This is 5. First we will add the 4 and the 6 part here. When we will add 4 and 6, it will give us the result of equivalent to 10. And as the 10 is greater than 9, so what we do is we need to add a 6 in it to make that result correct. So when we add a 6 here, we will get zeros here, and we will get a 1 carry to the next column. And if you perform the next column, the result is here, this is 8 and this is 7. So when you add both of them, again we will get a result which is greater than 9, and there is also a carry from the previous column too. So what we do is we again add 6 here. So when we will add 6 here, the final result will become 6. Overall result will become 6 with a carry on. That carry will move to the next column, and then next column the actual addition is between 1 and 5, but we have again a carry from the previous column, so we also have to consider it. So once we have, this is 1, this is 5, and we have a 1 carry, so if we add all of them, we will get a result of 7. So as 7 is smaller than 9, so we don't need to add a +6 term here. So this will give us 7. So this is actually 7, this is 6, and this is 0. So in this way we will get the exact result. So what we have to do is, if the result is greater than a 9, we just need to add a 6, and if there is a carry generated, we have to transfer that carry to the next column. There are many other decimal codes which we use in different hardwares. Most of them are specific to certain hardware, like 8 for -2 -1, 2 for 2 1, and then the XS3, then we have the gray codes. All of them have certain properties related to how they are built up. So you can move from one number to the next in a following a certain binary code. For example, the BCD and the 8 4 minus 2 minus 1 and 2 4 2 1, these are actually the weights. These are examples of the weighted codes. While there are certain like XS3 and 2421 which are called the self-complementing codes. If you see that, if this is the decimal equivalent and its XS3 equivalent code is this represented in this way, and you take this 9 complement, it's similar to taking the ones complement of this one. So both of them complement are complementing. So these are known as the self-complementing codes. This is a table in which most of the common codes are related. That how do you represent them? For example, this is the BCD. We have studied the BCD one, that it represents from 0 up till 9, and the remaining sequence is unused. Similarly, there are few other codes that are also used related to certain hardware. Say for example, if we are discussing this 8 4 minus 2 minus 1, this is simple. In this, these are actually the weights which are multiplied by this sequence. Say if you want to represent this, that what's its equivalent decimal, what you do is represent multiply this 8 term with this one first, this 4 with 1, then minus 2 with 1, then minus 1 with 0, and then you just add them. So it will give you the equivalent of its decimal, which is 2 in this case. Similarly, if you are studying the 2421 binary code, in this case the weights are this 2 4 2 1. So you multiply 2 with the 1, then 4 with the 1, then 0 with the 2, and then 1 with the 1, and then you just add them. This will give you an equivalent of 7. So this will be equivalent to the 7 in the decimal digits. If you see that in all these codes, there are some unused sequence. In just like in the BCD one, there is also a list of unused sequence in all of them. It means that all of them are represented in 4 bits, but all of the combinations are not used most all of the time. So only the combination which are defined above this line are used, while the remaining combinations are not used in this representation. Similarly, there is an other code which is known as the gray code. In the gray code, what we do is that if you represent any number from representing any number in gray code, then the next number is generated by changing only the one bit. So if you change only the one bit, then you can move the next. So if you see that this is 0 0 0, if in the next representation, if you're representing 1, only the 1 bit's value is changed. Similarly, from here to here, you see that only 1 bit value is changed. Similarly, again from next one, it's only 1 bit value is changed. So in a gray sequence, from one number to another, when you move in the decimal equivalent, only the 1 bit in the gray representation change, the other bits don't change. So this kind of representation is useful when you require a very minimum change in the hardware part, because you have to only change 1 bit. And how that bit is changed, you can see from this example, that this is the actually the binary equivalent of 7. So if you want to have its gray code, what you do is you take the exclusive OR of the first 2 bits, and if the 2 bits are the same, then we will get a 0 result here. Similarly, between 2 and 3, and similarly between 3 and 4, the last bit will become the same position. So it will give us a code of 0 1 0 0, or which is equivalent to the 7th value in the gray code. So this is how the gray code is performed. In gray code, we have all the values from 0 up till the 15th. We will be utilizing this in the game map thing, which we'll be discussing in the next chapter. There is an other important code which you are very familiar with, which is known as the ASCII code. Actually, the ASCII codes is used to represent the characters in our computer system or in digital systems. So there are specific codes for different characters which are predefined, and we just represent, if we have to represent a certain number or a certain character, you just write its equivalent ASCII code. So generally, an ASCII is represented in a 7-bit format. So we, for different types of characters and different types of alphabets and numbers, there is a specific code, and we just use that code to represent a different thing. For example, if we just look at the table of this is standard ASCII table, the bits are represented in this way. And if you see that their sequence, you combine this 000 and this one, this will represent a certain character. Like say if you are using the enter character or delete, or you are representing any certain brackets or a number, you have a different ASCII code for capital H, you have a different ASCII code for the small h. So there are many things that you can represent in this ASCII code, and it is standard in most of the hardware system, and we commonly use it to represent any character. And there are also some control characters too. You don't need to remember all these characters. Just you can, whenever you need to represent an ASCII system or number in an ASCII character, you just use this table and use its equivalent ASCII code. Then this is last important thing. This is known as the error detecting code. We will discuss this through the example of an ASCII character, but it is equally applicable to many other applications. Generally, what we do is when we have to transmit a data from one computer to another, say we have a one PC here and we have a other PC here. We need to communicate between the two PCs. So what we do is that for representing or communicating between the two PCs, we have to make sure that the data that we have sent from the first one to the next one is of the same thing, is you can say as an authentication thing, that the data which was sent from the computer A to the computer B is the correct one. There's no change in the data, because the actual communication, when it took place, there is a very high probability that there could be some error in the communication part, and that error could lead to a different value, because what we are sending here is just a value of 1 and 0, and we have already defined that each 1 and 0 are represented by certain logic levels. So due to some noise and or some communication problems, the thing that is reaching the B part may be of the different thing. So in this case, what we do is we define a systematic procedure in which we can check that whether there is some fault in the system or there is some error in the system or not. This method only detects that if there is some error or not. This method doesn't you can say correct that code, it only detects the error. What we do is that there are two types of error that could occur in a system. We use both of them to discuss that how we can detect this error thing. Say we have a number whose ASCII is represented in this 7-bit format. This is actually an ASCII of capital A. It is represented in this way. What we do in ASCII is we add to this number an additional 1 bit. Or to the MSB side, we add an additional 1 bit. This 1 bit determines that whether our result is correct or not. How we do is that we do it in two different ways. One is with the even parity and the second one is with the odd parity. In the even parity, what we have to do is that we have to make the whole thing, this part combined with this part. If we have even number of ones, then this value will be 0. if this code has odd number of 1, then we will put that value equal to 1, so that the whole number of ones in combining with this 7 bits and this 1 bit part, if the whole number is should be equal to the number of ones should be equal to even number in the form of say 2, 4, 6 in this way. So what we do is that in this number we add an extra bit here, and we check that we count the number of ones here. If say the number of ones is already even in this case, and what we do is that we will put that the value of the additional parity bit equal to 0. And if we have a number of ones that are equal to odd, say this is the number that we wanted to transmit, and what we did was we add an extra bit here in this format. We counted that there are 3 ones here, 1, 2, 3. There are 3 ones here. So for the even parity, we have to make the whole number of combination of 1 equal to even. So what we do is we add this parity value or set this parity value to 1. Now the total number of 1 in this whole combination will be equal to even, like this: 1, 2, 3, 4. So this will represent an even parity. So what we do is in for the number, any number that we want to represent, what we do is we add an extra bit. This bit represents the parity bit, and we set the parity bit value in such a way that the total number of ones become even for this even parity case. Say, because if the numbers of ones are already even, then this parity bit will have a value of 0. If the number of digits in number of ones in this range or odd, then we will have a 1 here, so that that will make the all number of ones equal to the even here, which is equal to 4 here: 1, 2, 3, 4. Similar to the even parity, we have an other check which we often use, which is known as the odd parity. Whenever we are deciding any communication between the two systems, we generally in advance we mention that what kind of parity we will be using. Will it be the even parity or will it be the odd one? For the odd parity, what we do is that we have an additional. In this case, we will again add an additional 1 bit, and now we will be setting the value of this bit according to the odd parity. In the odd parity, what we do is that we have to make this whole combination of bits that we are representing here is that the number of ones should be odd here. For example, in this case, for the ASCII value is A, we know that there are 2 ones here already. One is this one, second one is this. So what we do is we set the parity value of equal to 1, so that the overall the number of ones here becomes the odd. We have odd here. For the ASCII value of t, we know that there are already odd number of ones here. So what we do is we set the parity value equal to 0. So in this way we define the value of the parity. You can see that this parity does not consider all kind of errors, or it is not made to detect all kind of error, because if there are, you can say, even number of errors, then that might go undetected, because there is, say, there are 2 bits values that are changed, then our system may not be possible for our system to detect the thing. But generally this is the very easiest way to detect the error, and that's why it's very common in the communication system. If you even use the serial communication between any 2 PCs, you can see that you select the value of a parity there, and the same process is used there. So because it's a very easy to use solution, it is still widely used. But it will not detect all kind of error, and the other thing is that it will be only detecting the error, it will not be correcting them. So if you want to correct that error, then there are some other processes or other techniques that you have to utilize to make the error correct. This was from the chapter 1. Can you do read these pages for better understanding?